So now in this video we are going to look at the Zener diode. That is the schematic symbol. So it's like a rectifier diode, which just had the bar, but there's a couple of lines there that kind of look like a Z right there going up and down. If they were angled a little more, then they would be Schottky diodes. We would use them differently, and those have a lower forward voltage than rectifier diodes. The Zener diode, so it looks kind of like a Z. This has it's kind of a reverse breakdown voltage, but generally called the Zener voltage, where when you have it reverse bias, so cathode more positive, anode more negative, the black band there is towards the positive side right there. You exceed that voltage, at least get close to that voltage, current will start flowing through the Zener diode, and it flows pretty easy once you get to a high enough voltage. What that ultimately does is build up the voltage of the Zener diode at the cathode right there, because if the voltage tries to go up, it just passes current through, so limits the voltage. You can use this as a signal to something else, so it is a reference voltage. You need a higher supply voltage, probably about 2 volts or more, than what you want for your Zener voltage. The 5.1 volt Zener diode, I believe, is the most true to its Zener voltage, where you can put a wider amount of current flowing through it, higher or lower, and it will stay closer to its Zener voltage, 5.1 volts, than other ones, I believe to be true. So first off, let's go to the power supply, and we are wasting a lot of current right now because we're not doing anything. We're just setting a Zener voltage so we can measure it with the multimeter, and so that's one of the things I've been focusing on lately, is trying to get a reference voltage without wasting this much current using diode voltages. So I used a couple of rectifier diodes recently, forward biased, to kind of simulate a Zener diode. But now we're going to actually look at basically how effective these two Zener diodes are. The 3.3, I just grabbed it out of a kit. It's not one I usually use a lot, so I'll probably put it back in this kit. I just bought this from eBay. I got a whole bunch of values cheap. One of the bags had the wrong value inside from what they wrote, so that may happen. But in case, if you have like a loop like this, sometimes I show that in videos, but people don't seem to watch those videos. You can get close enough. On the component there, you'll see a C on it, and then 3V3. So they have V instead of voltage there for 3.3 volt Zener diode. They moved that V to where a dot would be, because you might mistake that dot maybe as a smear or something, but it's pretty clear that is a V. That's handwritten, so it's kind of sloppy. So that's one reason why they use V for voltage as the decimal point. So now we have the multimeter here to measure voltage. All I have to do for this meter is set it to V. We're measuring DC, which it's already set to. If we need to measure AC, we press it once, but we're going to measure DC. And if I cover this, the backlight comes on, but I know it's kind of hard to see there. Red probe, we only have to move it for high current. We don't have to move it for this video. And this is the circuitry that got me thinking of Zener diodes, actually before I started making the videos. But I'm going to hold it down there so we don't lose it. So this is the 5.1 volt, and that's 1,000 ohm resistor. So ultimately that's setting the current. The supply voltage of 15 volts right there, or 12 volts, sorry. And I was using 15 volts in an earlier video. 12 volts there. And so the Zener diode is dropping about 5.1 volts. At this higher voltage though, you can see it's a little bit higher than 5.1. But that's a 1,000 ohm resistor. It has the rest of the voltage across it. So whatever that's the voltage there. When you divide it by 1,000, that lets us know there's about 6.7 milliamps of current approximately going through there. So let's remember 7. Here we should see this is 3.3, but there you can see it's quite a bit higher than 3.3. So this isn't as solid. This isn't completely solid, but this is even worse when it comes to the amount that it will drift. So we had a little less than 7 milliamps of current up there, and we'll get the voltage across here once I get some good connection. So I got like 8.3. So I think we can round those to like 8 and 7, I believe. Is that what? Yeah, it was a little bit below 7 here. That was a little bit above 8. So I think we can add 8 plus 7, and what is that, 15, I believe. And there you can see this actually says 15 milliamps of current. I think I got my math right there. So now let's go down to a lower voltage. So since we have a 5.1 volt Zener diode, let's go to 7 volts. And now you can see we don't have near as much current flowing through because we lowered the supply voltage. There's less voltage across the resistors. We're not going to worry about how much is going through there. We already did that math. There you can see, yeah, we're just a tad bit above 5.1 volts, but it's holding like really steady. We got a fairly reliable voltage there. We know it'll drift a little. And there, remember, it was like 3.5 volts at that higher voltage. Now it's just a little bit below that 3.3 volts, about a tenth of a volt right there. So it will drift more. Now, I'm just going to turn that off because I'm done measuring for the moment. But I'm interested in the 10,000 ohm resistor right here. So my previous video, I was trying to limit current, but I wasn't using Zener diodes. I was using rectifier diodes. They're forward voltage. Remember, we're using the reverse voltage here. So let's see here how well the 5.1 volt will do. This is 10,000 ohm resistor right there. You can see that it's not showing any current flowing through there, and it should be, less than a milliamp of current. So we get the voltage across there. There, you can see it's not 5.1, but still it's kind of close to 5 there. So we won't want to draw any current from this going to other circuitry. It's a reference voltage. We want, like an op amp or something. Maybe even a transistor will work perfectly fine. And we'll go up to 12 volts. Again, we could go up to 15 now because we're using a 10K resistor there. Current is very low. Again, it's not even showing 1 milliamp on the power supply. And there you can see, really close to 5.1 there. So, pretty good for the 5.1 volt Zener diode. I believe the reason why, this is an old schematic that I showed earlier, I believe the reason why I may have used the 1000 is because of the 3.3, Zener diode right there. So, I just measured this a little bit before I made the video. There you can see it's doing horrible. That's with 12 volts at the power supply. That's not even 5 volts. We're not getting that Zener voltage. So again, as I said before, the I believe even higher value Zener diodes, the 5.1 is, I believe, the most solid, where it will hold its Zener voltage the most. I believe even higher ones will drift more, But as long as you got a steady or a certain amount of current going through it, you should get close to its reference voltage. And to tie into its exact reference voltage and or to not let it drift at all, you use a current source to make sure that the same amount of current is always flowing through it. And then you won't want the load drawing any current too. That would help stabilize it. So in any case, that's the Zener diode. You get a reference voltage. That is the main takeaway. It is not perfect though, as we saw in this video. That's one reason why I made this video. As we saw, we probably need, we might have like other values we can use, but compared to a 10K resistor, we needed a 1K resistor instead to get close to a Zener voltage. Whether we were down to like 5 volts or, 7 volts or up to 12 volts. And we would have gone down to 5 volts, but that would be the Zener voltage here. So that's kind of pointless. We got to go up a little bit more so that current will flow through that resistor and also the Zener diode to make sure to build up that voltage. Otherwise, the voltage might go down rapidly. And of course, if you have 4 volts, there's no way you can build up more than 4 volts at this point right there. So you need that current flow to lock in the voltage based on the Zener voltage of the Zener diode. So again, it's maybe the only diode that you use reverse bias where you purposely let current flow through it. I know there's other kinds, but they might pop up if you look at certain specialty circuits or something. But for the most part, if you're making circuits yourself and you're learning electronics, odds are probably Zener diode's the only one you're going to have reverse bias where you're letting current flow through. rectifier diodes, if they're reverse bias, they overheat really quickly if current's like flowing through them, and you might fry them. Same with Schottky diodes. So Zener diodes probably the only one you want to use reverse bias, and definitely the only one you want to try to get a voltage, reference voltage out of it when you have a current going through it reverse bias. So in any case, hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.